Okay, so the question, how do we access assignment 2? It's on the course website. If you just go to the course website and click on the assignments arrow, it should open all the assignments. Okay. Yeah, so I'm not posting it on EdSTEM. It's only going to be on the course website because if there are any changes, unfortunately in EdSTEM, I decided to just put it in one place so that these changes are synced across all platforms. Okay. All right. So let's get started. So where were we? Maybe let me make a note of that. Okay. And it's due next Monday. And I'll have the grades for assignment 1 out today. And also, just as an announcement, I'll actually send out a survey on EdSTEM today. Please fill it out. I want some feedback on how the class is going, how this remote instruction thing is working, and if there are any changes that we can do to make things better. Okay, so just watch out for that, and please fill it out as soon as you can and as much detail as you can. Okay, so last class we talked about we continued our discussion on online learning algorithms. In particular, we talked about the weighted majority algorithm, which gave us some bounds on the regret. It was getting a factor of 2.4 plus something over what the best expert does. But it is not a no regret algorithm in the sense that we define, right? So an algorithm is no regret if the average gap with the best expert was going to 0 as you play the game more and more. So in some sense, as you play the game repeatedly, you should get as close to the best expert as possible. And for that purpose, we introduced the multiplicative weights update algorithm. We said it does better. And today, let's try and show that. What does it mean to say it does better? How does it do better? And then I want to talk about 2 applications of the multiplicative weights method. It has tons of applications. You can write a whole book just on that. You can teach a whole course on that if you want to. But I will highlight 2 applications which are kind of connected to the rest of the course as we are discussing. And for the applications, I probably won't go into too much detail because I really want to stress the algorithmic ideas and not the underlying analysis, which is important, but hopefully you can fill out those details based on what we are covering for multiplicative weights. Okay, so just as a recall, what was the multiplicative weights algorithm? So you started out by giving a weight of 1 to each expert, right? That's it. So each expert has a weight of 1 and then on each day, as we learn about the losses of the experts, we update their weights. If an expert is making a lot of mistakes, then we penalize them, right? Their weight keeps going to 0. And why are these weights important? We make our predictions based on these weights. In the sense that in each day, we pick an expert with probability proportional to their weight and just follow that expert. So back, maybe on the first day itself, some of you said follow the leader kind of algorithm, right? You just follow a leader. So multiplicative weights is a little bit like that, but you follow the leader in this probabilistic way, and if a person has made fewer mistakes, then they are more likely to be followed. It's not deterministic, but they are more likely to be followed. Okay. And some notation. So our algorithm is randomized. Right? So each day we make a probabilistic prediction. We follow expert 1 with some probability, expert 2 with some probability, and so on. As a result, our loss is also randomized. And what we're interested in is the expected loss we incur over time. So let L of t denote the expected loss of our algorithm, the multiplicative weights method, on day 1 or day t. And let A of t be the total expected loss over the first t days. And this is the end of day t. Okay? And as usual, A star of t denotes the loss of the best expert. How well is the best expert doing? And what we'll show today is that if we initiate multiplicative weights method with this epsilon parameter, where you penalize each expert with the parameter with something like epsilon, then the performance, the expected performance of the algorithm is at most a 1 plus epsilon factor of the best expert plus some additive log d or epsilon. Okay. And once you have this generic bound, so here we're not setting epsilon to be anything. You can set epsilon to be 0.1, 0.3, anything you want. And once you do that, okay, so I should say that epsilon has to be something less than a half. And you see that epsilon is 1 over square root t ln d. You get a of t, the expected loss, is at most a star of t plus 2 times square root log t. Okay, this is just kind of initiating the previous general bound with this specific epsilon. Okay. Any questions about the basic analysis setup and the algorithm, and how we are going to try and show that it performs remarkably well? If there's anything not clear about the algorithm, now is the time to say it, because we are going to dig into its analysis pretty soon. Okay. All right.
For these algorithms, we update the weights when we make a mistake personally, right?
Right.
So, but why do we not update weights just on every iteration, regardless of not whether we went with the expert's advice or not? Like, so if an expert made a mistake, even if we didn't use that in our prediction.
Oh, so the weights are updated irrespective of we make a mistake or not. Whenever the expert makes a mistake, their weight is updated.
Okay.
Right, so yeah, that's a good point. So like here, this is for all experts. So this second line is kind of completely independent of the first line. The second line is deterministic. I think this was a point that was made towards the end of the towards the end of the last lecture, is that, and this is an important distinction, that the only randomness is in the prediction. The weights evolve in a deterministic way. Okay, so whenever expert makes a mistake, their weight gets penalized. That's it. Okay, and our performance is the one which is randomized. And the one small difference from last lecture is that if you go back to last lecture, we had this sort of case analysis, right? If they didn't make a mistake, we kept the weight the same, right? And that's the same as saying that just writing it in one equation is like 1 minus epsilon times L times W. So for instance, if they didn't make a mistake and this loss was 0, that means their weight is staying the same. If they made a mistake and the loss was 1, then their weight decreased by a factor of epsilon, of 1 minus epsilon. Any other questions? Okay, so let's try and show this. And the proof is actually very similar to what we did, for in the analysis of the weighted majority algorithm. It goes via potential and the same potential, in fact. The main idea, track W of t, which is summation okay. And once again, I want to emphasize the analysis, because many times you might not be able to use this black box bound that we have. A of t is 1 plus epsilon times a star of t, and you might have to tweak it to understand how you might adapt it to your specific case. For instance, in one of the applications, you should not really use this bound, but you should use a more refined one, which is basically just change one line in the proof and you get this amazing result. right? So that's why I want you to understand how to analyze these algorithms, because often you'll have to adapt them. Okay, so how do we track this way? I want to relate this potential function to the performance of my algorithm or of our algorithm, right? So first step, let's try and calculate what this loss is. So what is this expected loss that we have, right? So this is expected loss on day t. So which we can think of as, what's the meaning of expectation? Probability even was picked, or let's say even was followed, times the loss of the first expert on that day, right? Plus probability, E2 was followed, times L of 2 comma T, plus so on. Okay, so we're just computing the expectation directly. And what is the probability that even was followed? What's the expression for that? Can anyone tell me? We know it is proportional to their weight. So this is proportional to W of t minus 1 comma 1. So that means that probability that EI was followed is exactly W of t minus 1 comma I divided by the sum of the weights. Right? So if I tell you that I want one to be picked with probability proportional to half, and the second person to be picked with probability proportional to 1, that means those are the relative odds, right? So you have to add up all these numbers to get something which is really a probability distribution. Okay, but this is exactly just the way we define the weight. That's essentially what we have, right? Okay, so let's put these two things together, and we have that the expected loss that we incur is exactly 1 over W of t minus 1 times summation I equals 1 to t of okay. All right. Any questions? Okay. So the nice thing now is we know what W of t comma I is, right? It's 1 minus epsilon right? So that's how much we're changing the weight. Okay, so let me expand this out a little. So you get this minus epsilon times all right. So what can I do now? Any suggestions? So my goal is to relate how the weight changes to the loss that the algorithm incurs. So I have this equation relating my loss to how the weights are there on the previous day, and here I have an equation for how the weights are evolving, right? So what happens if I add up all of the weights? Okay, so if I add up all of these weights, then I get summation I plus 1 to d w of d comma I, which is exactly the total weight on day t. The first terms will give me the total weight on the previous day. Maybe okay, and then minus epsilon times okay, I added up everything. And now this is just the total weight on the previous on today, total weight on the previous day, and how about this one? We know exactly what that is. It's exactly the total weight on the previous day times the loss that I incurred on day t. Right? So, in essence, we just showed this very nice relation between how much loss we are incurring and how the weights are changing. Right? So if you incur too much loss on a single day, then your weight, total weight, has dropped significantly. Okay, does this make sense? Any questions about this simple arithmetic? So, so this is all very good, and we are almost done, except that, as before, as in the analysis of WMA, we have some nice iterative way on how the weights are evolving, and we would just like to multiply them and be done with it. But unfortunately, so somehow here things are not as nice because the factor is not a constant. Like, earlier we said each mistake costed you like 3/4. Reduce your weight by 3/4 or something like that. But here it's a little bit more nuanced. So we have to sort of do some more simple manipulation from here on to get the final result. So let me not belabor those calculations. But this is a trick that, if you have done any course in calculus or something like that, you might have seen, which is that when you have some multiplicative expression like this, it's often easier to write it as something in the exponent instead of just a multiplicative thing. Okay? So what do I mean? So here's a simple fact. So let's say fact 1 is 1 minus x is less than or equal to e to the minus x for all x. For any real number, 1 minus x is at most e to the minus x. Okay? So this implies that w of t is less than or equal to and the reason I'm doing it is now if I iterate this equation, what happens? Any guesses? Something nice happens. So what would happen? So I get times e to the minus epsilon times L of right? Okay. And the nice thing with exponential is that multiplying them is basically adding things in the exponent. Oops. Okay. So this is very cool. So now this total sum of this expected losses is exactly the loss of our algorithm that we're interested in, right? And W of 0 is just D. So what have we shown? We showed that the total weight that we have after T days is kind of related, is upper bounded to how much loss we incur. Right, so if our algorithm incurred a lot of loss, then the total weight is really small. Right? Any questions about that? Okay, so now what can I do after this? I have an upper bound and I need to somehow connect it to the performance of the best expert. He is one of those D people sitting there. I want to connect the total weight to the performance of that expert in our game. And from now on, this is exactly like our analysis of the weighted majority algorithm. So what can I do to proceed from here? Any suggestions? So I want to say that, okay, so the total weight is upper bounded by the performance of our loss function, but at the same time, we can also relate it to what each expert is doing. Okay, so in particular, I want to say that, well, we clearly know that is at least this much. Right, the weight after day T is, for any expert I, is at least their weight. But what is the weight of that expert after T days? Remember, our algorithm is deterministic, right? It just updates the weight in a fixed way. So what can you tell me about their weight after T days? Right, every mistake they make costs them 1 minus epsilon in the weight. So after T days, their weight is, what can I say about their weight? Okay, so their weight is exactly right. So no? So in the sense that, so if they incur a total loss of some number, then their weight is just 1 minus epsilon raised to that power. Right? Each mistake costs them 1 minus epsilon. So if they made some, x number of mistakes, their weight would be 1 minus epsilon raised to the power x. So this is just, let's say the performance of the best of the expert until day T. Performance of the ith expert until day T. Okay? Any questions about this? Alright, so we have these two simple claims, very analogous to what we had for the multiplicative weighted majority algorithm, right? The analysis there was simple enough, and here it's following the same blueprint. And we just have these two things, and let's connect them together, right? So what we have is that these two together imply that the performance for any I, the performance of the best expert, can be controlled via this inequality. Okay? And what does this say? So now, I have some inequality which relates the performance of our algorithm to that of, of any expert, right? So maybe what I can, it seems like some inequalities is a bit weird, but just as for the weighted majority algorithms analysis, we have something in the exponent, so let's take logarithms to connect them. So this implies that a of t comma I times ln 1 minus epsilon is at most so ln is the natural logarithm, of course, plus ln t. Okay? And this implies just basically what we want. Okay, so I moved the a of this epsilon a of t to the other side and did some elementary manipulations to get that the performance of our algorithm is bounded by something like this times the performance of any expert. Okay, so we know this is true for every expert I. So in particular, it should be true for the best expert, right? So this implies that a of t is at most ln of 1 minus epsilon divided by epsilon times the loss of the best expert plus this guy. Okay? Because a star of t is just loss of the best expert. And we have the inequality for every person, so it should also be true for the best expert. Okay? Any questions? Now, now comes another, like, let's say, fact, from elementary calculus that basically ln of, 1 minus x divided by x is less than or equal to 1 plus x for x less than or equal to half. Okay? You can just plot the curves and see this thing, or if you can use the expansion of the logarithm function to get this, but that's not at all important for us. And as a result, we just get a of t is at most 1 plus epsilon times a star of t plus ln d by epsilon. Okay? So that's great. That's the entire analysis of the weighted, of the multiplicative weights update algorithm, right? So let's do a quick recap. So the main thing here is to track some potential function, and the potential function is exactly the same as before, which was the sum of the weights that we have. And there's some kind of magic that happens when you write down the expression for the expected loss, right? When we write down the expression for the expected loss, we get this amazing equation relating the performance of our algorithm to that of to how the potential changes. So if your algorithm did badly, then your potential decreases a lot, right? Which is exactly what happened in the weighted majority algorithm too. So we said, if you make a mistake, then your total weight drops by 3/4, right? And this is saying something similar. Okay. All right, and you play with everything, and you end up with our final bar. Any questions?
I have a quick comment about the statement of the theorem and the corollary. I think there's a mismatch in.
Oh, let's go back. Let's see.
So you say when epsilon is 1 over root t log d. I think to get the error that you get in the corollary, you want the log d to be in the numerator. Like,
Oh yeah, you're right. Thank you.
but I was also curious, like, why, I don't know, why you're choosing this exactly.
Right.
I mean,
So let's go to that. Yeah. Let's sort of parse that.
like, you want epsilon going to 0 as t goes to infinity. Right.
Right. But also then, so let's see. Right. So this is proof of main theorem. You know, it's kind of a stretch, but we've seen something like this already in the course, right? Like where you had to balance two terms. Can you remind me where? So we have a of t is less than or equal to a star of t plus epsilon times a star of t plus ln d by epsilon. Okay, I'm just rewriting it. And we know that the total loss of the best expert is at most t. Each round they incur loss of at most one. It's kind of pessimistic, but you know, if I want a bound that just depends on the number of rounds, I can do that. Okay? And now we just have to balance these two terms, right? If I make epsilon to be very small, then this decreases, but then I'm incurring a penalty here.
Got it.
Right? So if I had to balance these two, go ahead.
And you set epsilon to log d over root t.
Yes, exactly. It's like, you know, it's like epsilon plus something to balance those two. You set it to be the geometric mean of those numbers. So if I set epsilon to be square root ln d by t, we get exactly the bound that we stated. And this balancing is a little bit, similar in spirit to what we did in the analysis of stochastic gradient descent, right? You should think of epsilon as some kind of step size. You know, how much you're changing the weight. It's really, in fact, it's not just a theoretical connection. You can view multiplicative weights update also as some variant of stochastic gradient descent in some weird space. It's called stochastic mirror descent. But it shouldn't even say stochastic, but it's basically some kind of online mirror descent. So you can view it that way and analyze it from there. That's not important for us, but basically we're matching this epsilon, we're balancing it in some way. And you should think of epsilon as some kind of step size. Okay? And the nice thing now is that we see that this is a no regret algorithm in the sense that the average loss, how far you are from the performance of the best expert, averaged over t goes to 0 as t goes to infinity. Right? So meaning it's a no regret algorithm. And we have the square root t ln d here. Okay? Alright, so any questions about the statement? So let me say, so let's try and digest this. And let's take a 5-minute break, and when we come back, I want to say a few remarks about this algorithm, and then we'll look at two applications. All right, so let's resume at 10:40. Yeah, poll is like, seems like it's pretty evenly split. And I'll ask for more detailed feedback on the EdSTEM thing so that I can learn more. Okay, so let me say a few things about some simple extensions and what's known about this multiplicative weights method, and then we'll jump into the applications, right? So let me say that some remarks. One is tight. best possible. Right, so in terms of regret, this bound of 2 times square root t ln d is the best possible. Maybe you can include the factor 2 in front, but like basically this dependence of square root t ln d is best possible. You cannot improve that in general. Okay, you might, you could have asked, we are getting square root t ln d, couldn't it have been like, maybe log t or something that's even much smaller? No, this is the best you can get. By any algorithm, not just multiplicative weights, but any algorithm. Okay, and the second thing is that, just for some kind of convention, we talked about the losses of each expert in each round, right? So the game we defined was something where it was 0, 1. Right? The losses are just either they're correct and then they get like the 0 loss, or they're wrong and then they get a penalty of 1. And in the homework, I asked you to show that the same thing, almost everything that we did works pretty much as is when the loss is even a number between 0, 1. Right? So like, your score could be 0.5, 0.1, 1, 0, anything in between, and you can still define regret and everything in the same way, right? The fact that these are discrete 0, 1 never played a role in our analysis. Okay? Any questions about that? And the one thing you have to do is change the algorithm to follow what we wrote here. You can't do a case analysis to say, okay, if they're wrong, then you decrease the weight by 1 minus epsilon. But basically, you have to change it so that, if they're very wrong, then you incur more of a penalty and things like that. It's just like a smoother way to penalize them. Okay? All right. Let's come down. That's number 1. So, same works. See assignment. Okay, and I want you to work it out. The third thing is, many times when you want to use it, and as we'll use it later, the 0, 1 is also a little bit like, artificial, right? The main thing is that there is some range where the losses occur. What if the losses were not bounded between 0, 1, but they're numbers between 0, 10? What would you do then? Right? I want to say that we can still apply the same thing and get something similar guarantees. And what would those guarantees be? Any suggestions? Suppose they are between some numbers 0, beta. What can we do then? Well, okay, let me not use beta, but maybe L. Okay. Well, I can do the same analysis, but just artificially scale the losses in my algorithm, right? I'll do everything the same, but I'll pretend as if my losses were scaled by a factor of L and run the same setup, right? Okay. So how do I handle this case? We have to be careful. We can't just use multiplicative weights as we defined above, because we have something like 1 minus epsilon times L of t comma I. Right? If this becomes negative, then it doesn't make sense, right? So the way to make sense of it is to just put an L, like sort of scale them so that they come back to 0, 1. Okay. And in general, really, you can do anything as long as the losses are bounded between some, let me not use, let's say they're bounded between some minus beta and beta. Okay. I tell you each loss is a number between minus 10, 10. It kind of, seems pathological to say the loss is a negative number, but imagine that just means that the person is getting a gain somehow, right? And even in that case, you want to sort of match the performance of the best expert. All right? here you can achieve a guarantee, which is essentially okay. So your regret scales by a factor of beta. Because you just divide everything by beta, maybe this is actually 4 beta, I think. Okay. So the way you do it is just scale everything by beta and then shift them a little bit so that they come back to 0, 1 and run the same algorithm. Okay, does it make sense? So, idea, scale, so define L bar of t comma I to be, let's say, okay, so if I define this new sort of theoretical losses, which are these numbers, then these are things in 0, 1, and I run multiplicative weights with these theoretical losses and then check my performance in the end. And you see that everything is just exactly the same. You just scale things by 2 beta, so you get 4 beta. Any questions about this? Okay. So it's in some sense versatile, but the main thing is that the losses in each round have to be bounded. That's the main constraint to keep in mind. As long as we have that, we get this no regret algorithm, which is going something like scales as this beta. Okay. All right. So those are the general remarks, and now let me say a few words about sort of how we can use it. Like, what are the applications of multiplicative weights? So I want to do 2 applications. Hopefully, I'll have time to go into some sufficient detail. Maybe not the full details, but I really want to stress the algorithmic ideas and not the full analysis for now. So, applications. There are lots of applications in learning. In fact, there are lots of applications in online learning. It kind of makes sense. We are kind of solving an online learning problem, right? And in the homework, in one of the problems, you're doing something which solves an online learning problem using multiplicative weights and gets a very different guarantee, right? And then it's especially useful for things where you want to get some guarantee, which is logarithmic in the dimension. Okay. It's useful for things like portfolio management in time series analysis. And as we'll see later in the class, you can use it for much more sophisticated learning, challenges like learning graphical models and so on. Right? And for instance, the idea in the last problem in the homework is something that I used relatively recently in my own research, even though that idea is very old. A small variant of that played a big role in designing a learning algorithm for graphical models. And we'll look at that result later on, but basically the title of the paper was something like Learning Graphical Models, which is a very important topic by itself, via multiplicative weights. Okay, so this is just to say that you can use it for learning problems which don't seem to have anything to do with online learning or learning with experts or things like that. And the other thing is that it's very useful by itself in solving things like linear programs. forget learning. I just give you a linear program and ask you to solve it. There is a solver for linear programs which is based on multiplicative weights. And it has some very important properties that are useful in many places. You can also solve all kinds of other crazy things, like solving semi-definite programs, SDPs, and so on. So these have nothing to do with algorithms. Learning. This is just applications in algorithms, like optimization algorithms. Okay. So today I want to talk about one application in optimization and one application in learning. All right. And the main thing to keep in mind of why I think, why this learning with experts framework and multiplicative weights in particular is so useful is that it's a very convenient tool / technique or formalization to use when you're trying to optimize or figure out probability distributions. Okay, so let me say a few words about that. So today we'll talk about optimization on simplex, right, or probability distributions, and on boost, which is a very important, practical important learning tool. Okay, and so MW is great when we need to find probability distributions. So imagine you had an optimization problem where you're trying to find the right probability distribution to use, right? You have, or select spread to use. You have a bunch of assets, you have some $1 million and you have, let's say, all kinds of stocks. I want to figure out how much percentage of my wealth should I invest in each of the stocks, right? So what I'm trying to figure out is a probability distribution on something. I want the right distribution of wealth, which is going to optimize my net growth for tomorrow or my expected growth for tomorrow. Okay? So in many such scenarios, when you're trying to optimize on probability distributions, when the things that you're working with are distributions, somehow multiplicative weights kind of keeps popping up. Does that make sense? Okay, it's a very sort of vague, intuitive thing, but just sort of happens all the time. So let's talk about the simplex. It's just a fancy term for probability distributions. So this is all. This is a subset. It's usually denoted delta D. Like triangle D is something like this, where is a set of all probability distributions on D elements. Okay, so I have some D elements and I have a probability distribution on top of that. Right, that's it. So one example to keep in mind is like somehow I have some X amount of money, I want to split it across my different assets. I have D assets to kind of spread my wealth on or put my wealth into, and each number then is like a proportion, right? It's like a probability, like a fraction that all together add up to 1, and each one is non-negative. Okay, and so let's consider this problem that shows up in many applications. So this doesn't have anything to do directly with learning, but it connects to what we did in the previous section and to multiplicative weights. So the problem is, I have some function defined on the simplex. okay? And my goal is to optimize that, like minimize that function. That's my goal. It's just like, plain old optimization problem, constrained optimization problem now, because I have to find something on the simplex and nothing else. So just to draw a picture, what does the simplex look like in 2 dimensions? Well, or let's actually do 3 dimensions. You have sort of this plane is the set. The shaded region is the simplex. Okay? And I have some function defined on it, and I want to minimize this. Maybe my f is something like, some crazy risk minimization function or wealth optimization thing that I have, right? If I invest so and so money in so and so stock, I have some model for how it will perform a year from now, and I want to find the best spread to optimize that. Okay? That's it. So this is my optimization problem. How can I solve it? Any suggestions? I mean, it's a constrained optimization problem, and let's say that f is even convex. Well, okay, the algorithm will work in any case, but let's assume f is even convex. So what can we say about it? What's one algorithm that we can try?
Can you use gradient descent?
We can do gradient descent, but then when you take a gradient step, you might go out of your constraint set.
But the constraint set is convex, right?
Right, so we have to use projected gradient descent basically.
Oh, okay, okay.
Right, so I mean just the name is different. So idea is we can use projected gradient descent. Okay, this does relatively well, but somehow it's not exactly as nice as what we're going to do. Okay, and I'm telling you that we can actually use multiplicative weights to get a very nice guarantee here. What do you mean? So in the analysis of gradient descent, we talked about the case where f is convex, right? And we also assume that f was smooth or kind of Lipschitz and things like that. Okay. And when we are talking about the simplex, right, the geometry is important. Like somehow all the constraints we have are sort of linear constraint. I have a linear equation on my space, right? The sum of the numbers is 1. And suppose my function is not exactly Lipschitz, like when I change something, it might change a lot. But it's Lipschitz in the sense that when I change a single coordinate a little bit, the function doesn't change too much. Okay? So one way to say that is if I look at my gradient of my function, and if I change the one coordinate from 0.2 to 0.1, I want to say that the value of the function doesn't change by more than 0.1. Okay, something like that. So it's some kind of it's kind of like a Lipschitz constant, but it's really working in this infinity space. So what do I mean by this? This is equal to the maximum value of the gradient's absolute value in any coordinate. Okay. So when we were optimizing convex functions, we said, it sort of makes sense to think the function is Lipschitz, which is a little bit like saying the gradient is bounded. Here the gradient is bounded, sure, but I have something stronger or weaker but incomparable in the sense that each coordinate of the gradient is bounded. Okay, so let's say I tell you that each coordinate of the gradient is at most 1. Okay, so for example, if f of p is p1 squared plus p2 squared up to pd squared. Okay, now what can you, the gradient is 2 times p1, 2 times p2, 2 times pd. Okay, so what's the maximum L2 norm of the gradient on the simplex? Well, actually, that's well, let's see. So I want to say that here this guy is at most 1, right? That's true. Each coordinate is always going to be at most 1 or 2. Sorry. Okay. So in many cases, when you're optimizing on the simplex, you might end up with trying to optimize functions where this is true. And one thing to keep in mind is that when we have something like this, this only implies that the L2 norm of my function of the gradient is at most L times square root 2. So like when we use gradient descent for this function, you might end up with a dependence which is something like scales as d instead of what we're going to do. Okay, but hold on to that part for a few minutes. Okay, so we're going to analyze the algorithm in this setup where I tell you that each coordinate of the gradient is at most L, some number L. And we're going to do play some weird mind game and end up with an algorithm for this problem using multiplicative weights. So how can I do that? The analysis is perhaps less important than trying to conjure up this game, which will actually help us design an algorithm for this. Alright, so what are we trying to do? Let's just see. So we're trying to minimize this function, but on the simplex. Now let's go back to one of the main algorithms that we looked at in the first section of the course, which was gradient descent. So there we said, you start out with some vector, and then, for each iteration, t equals 1 through t, you do something, which is like you update your current iterate as your previous iterate minus some step size times the gradient. So you take a step along the negative of the direction, right? And now, inspired by the multiplicative weights update method that we just saw, I'm going to talk about a variant of this algorithm which is much more powerful or gives you much stronger guarantee for the specific optimization problem. So instead here you're doing an additive step along the negative of the gradient, right? You're decreasing the vector additively. So it's an additive update. But we can also ask for something stronger or different, which is to do a multiplicative update based on the gradient. So that leads to the following. Let me call it the multiplicative gradient descent algorithm. So what is that? So I want to say that for each iteration, I'm going to update each coordinate of my vector multiplicatively based on the gradient. So I compute the gradient of my vector just as before, right? And look at that coordinate. So before we were just subtracting the ith coordinate from the previous ith coordinate, but now I'm going to multiply the previous one with something depending on the gradient. Okay, so this is what I really want to do. And here I'm introducing the proportionality symbol because we need to make sure that after doing this multiplicative update, we are back in the space of probability distributions, right? So the two caveats here. First is that we have to come back to the space of probability distributions, and the other thing is that we need to make sure these numbers that we are writing down here when we multiply things, they are non-negative, right? So how do I do that? You have to be a little bit subtle. If these gradients were all bounded, between 0 and 1, then you can just use this update. But all we know about them, they are numbers between minus L, L, right? Each entry of the gradient is at most L in absolute value. So to mitigate that, to kind of exploit that, let's use the scaling trick in the definition of multiplicative weights update method. So let me define L of t comma I. You'll see why I'm calling it L of t comma I soon, as just the gradient, the ith coordinate, and sort of the normalization of it, which brings it back to the 0, 1 space as okay. And now I'm going to update my current vector exactly as this. Okay. So I have a probability vector pt minus 1. Now I multiply each coordinate with this specific 1 minus epsilon L bar t comma I term. And then I renormalize everything to make it a probability distribution. Right? So if I were to rewrite it, then it would be something like this. So here's the multiplicative gradient descent algorithm. So let me write this as L of t comma I and p bar t of I is exactly 1 minus epsilon L bar t comma I times the ith coordinate. But then I have to divide everything by their sum so that I get back something which is a probability vector. Okay. But let me also break this up into multiple steps so that I can make a connection to multiplicative weights more directly. So what do I mean? It's the same algorithm, but I'm going to rewrite this in slightly different way, right? So in particular, what I'm going to do is I'm going to define these weights just as we did for multiplicative weights method, which we will use to define the current iterate of our algorithm. So we start with weights being all ones, okay? And I now make it I define the update of the weights just as we did for multiplicative weights, right? And I'm basically done now as I write down the ith coordinate of my current iterate as something proportional to these weights. So it's exactly what you get by normalizing these weights. And the main thing you should keep in mind is that at the end of the day, after all of this, what the algorithm is really doing is you're kind of doing a gradient update but in a multiplicative fashion. So pt of I is roughly 1 minus something times the gradient of f at pt minus 1 diet coordinate times pt minus 1. Okay, it's not exactly that because you're scaling some things and shifting some things so that you remain in 0, 1, but that's about it. Okay, hold on. So let me now box this. This is our multiplicative variant of the gradient descent method. Okay, you know, it's some algorithm, and you should think of this epsilon as some kind of step size for multiplicative gradient descent. Just as we had a step size in gradient descent, now we have some kind of other step size for multiplicative gradient descent. And what we'll show is that this multiplicative gradient descent does very well in the case we are looking at. So in particular, after t iterations, okay, if I look at the sequence of iterates that my algorithm picks. So remember that the sequence of iterates are these p's. Those are the ones that we are trying, those are optimizers. Right? Okay. So if you focus on that, then the min of f of p of t, or t equals 1 to t, among all the t iterates, there is one whose minimum is very close to the absolute best, right? Which is okay, plus some loss term. And what is that loss term? It's as you can imagine, it's exactly plus let me, after t iterations, it's basically square root of L times ln t divided by t. Okay, so what is this saying? It's saying that after t iterations, you're finding, or you can look at your iterates to find a value which minimizes the function or which gets close to the minimum value of the function in the simplex up to this term. Okay. So as a corollary, and here we are going to set epsilon to be something like square root ln d by t. Okay, the step size should be something like that. And as a corollary, what we get is to get after t equals ln d by delta squared iterations. Okay, if I run my algorithm for something like L squared times logarithm in d over delta squared iterations, then I can find a point, let's say p bar, whose value is delta close to the least possible value of the function on the simplex. Okay, so we're getting very close to the minimum value up to delta close. And the most noticeable thing here is that the dependence on the dimension is logarithmic. So I'm optimizing in d-dimensional space, but I'm only running it for log d many iterations, if you think of L and delta as constant. And for this particular normalization, if instead of using multiplicative gradient descent as we defined it here, as inspired by our multiplicative weights update method, if you used plain vanilla gradient descent, you can also get some kind of convergence, but the number of steps needed would be something like d over delta square. So your number of steps would grow linearly with the dimension, whereas the multiplicative gradient descent, the number of steps grows logarithmically with the number of with the dimension, which is very remarkable. Okay. All right. So now let's try and understand or prove this theorem. And the proof is really just kind of reinterpreting this multiplicative gradient descent back in the language of learning with experts and applying our regret bound that we proved for multiplicative updates. Okay, so let's see how to do that. So analysis of multiplicative gradient descent. Okay. So for the analysis, we are going to imagine we are playing a learning with experts game. There is no learning with experts game. In the algorithm, there's nothing happening like that. But we're going to imagine there is a learning with experts game, and in a way so that what you have written down here is exactly what would show up in the update if you apply multiplicative weights method there. So I'm going to say that you have experts E1, E2, E3 up to ED. Okay, and you have each day, right? And we started out with the probability vector P0 being just 1 over D. Okay, so that corresponds to the weights being all ones. Now, how do I define the losses, right? So there is this phenomenal power in the regret minimization framework, right? So the guarantee for multiplicative weights update holds no matter how the losses are defined. They can depend arbitrarily on what you have done so far, but still we get some reasonable guarantee out of it. So what can we define the losses as? So if you look at this update, so it's kind of giving away the answer in that I called L of t comma I the gradient, right? So that's exactly what we're going to do. So I have a P0. I'm going to say that the loss for the day one, the losses are exactly determined by the gradient. So I look at the first coordinate of the gradient, that's the loss of the first expert. Okay, the second coordinate of the gradient, that's the loss of this second expert, and so on. Okay, so I'm interpreting the coordinates of the gradient as the losses of the expert. The first thing is we are interpreting coordinates of the vector as experts. They're giving us some information for what the losses should be. And now the elements of the gradient are the losses. Okay, so these are the losses for day one. Okay, and once you do this, you update your weights, and then you get a new probability vector which is proportional to the losses for that day. Sorry, to the weights for that day. And then I once again determine the losses, which are exactly the gradients. So the main thing to keep in mind here is that we make our prediction in the multiplicative weights update method after the losses are revealed to us, right? So each expert gets some loss, and then we are allowed to update our weights. So that's exactly what we are doing here. So this is day 2, day 3. So we make our prediction before the losses are revealed, and we update our weights after the losses are revealed. So this is once again the same thing. these are just numbers at this point and we are interpreting them as losses. But let's see what we gain out of this interpretation, right? You go all the way up to day t, and these are the losses there. Okay, and so now we have some regret guarantee for us, right? So the regret guarantee tells us something about the performance of the multiplicative weights update method, which is exactly this algorithm, right? It goes through the exact same iteration, so the p's are rated in the same way, and the best loss that any expert achieves. So what's the best loss of any expert? Let's look at the losses of each of the experts. If you add them up, what you get are sum of the gradients, right? This is total loss. I can add up the losses of all the experts, and I would get, just sum of the gradients in the first coordinate, sum of the gradients in the second coordinate, and so on. Okay? Alright, so these are the total losses of each expert. But how about the loss of our algorithm, right? So the expected loss of the multiplicative weights method on day t is actually, so you pick each expert with some probability, and then that expert incurs a loss. So the expected loss would be, you have to look at the probabilities, right? So we just probability E1, sorry, this should be I, or let me, summation I equals 1 to D, probability EI is picked, right? Times the loss of the ith expert on day t, which is exactly the gradient, right? Okay. Now what is the probability that expert I is picked? It's proportional to the weight of that expert on that day, right? So it's WT minus 1 comma I divided by the total weight the previous day. So this is really just PT minus 1, the ith coordinate, times the gradient at coordinate. Okay? More compactly, I can write this as the inner product of the gradient at pt minus 1 with the probability vector that you had the previous iterate. Okay, so this is the expected loss of multiplicative weights update on each day. So the total loss of our algorithm is exactly the sum of the expected losses, which is okay, and we know that this is close to the loss of the best expert. So the loss of the best expert is the minimum entry in these total losses, right? So let's write that down. So it's at most min over I is 1 through D of looking at the gradient, adding it up across all the iterations and the ith coordinate. Okay, it's this quantity plus 4L times square root log D. Okay, so if I ran it with this update, I get something like this. So this is what we get out of using our rigid analysis for multiplicative weight method. And that's also what we get for the multiplicative gradient descent algorithm, because both are essentially the same. Now this seems somewhat useful but not quite, because our goal is to minimize the function f, right, on the simplex, and we have some weird inequality involving the gradients. How does the function f even come into this picture? How can I relate something about the global minimum of f from this inequality? But we can actually do that. So let me write a sequence of games. So let P star be a global minimizer of f. Maybe there are many things, just pick one, it doesn't matter. So the first inequality I'm claiming is the following. So here, if you look at this sum of the gradients, right? I can think of the vector which is sum of all the gradients over all the iterations. We know that my total loss is comparable to the minimum entry. Okay? My claim is that the minimum entry here of the sum of the gradients and the dth coordinate is at most, if I look at the sum of the gradients so far, of all the things that I've seen in the iterations, and P star. Okay, so P star is a point on the simplex. It's a probability distribution. And what this inequality is saying is that the minimum coordinate in the sum of the gradients in any vector is actually at most the inner product of that vector with a probability distribution. And the reason this is true is just because you can expand this out and look at each coordinate. We know each coordinate is at least the minimum, so you substitute the minimum and add them up. Okay? So let me write that down here. Proof. So summation t equals 1 to t, gradient. As I said, this is not really specific to the gradient, sum of the gradients. I'm going to just define u as the sum of the gradients. What we are saying is the inner product of u comma p star is just summation I equals 1 through t of ui and p star I. So this is at least the minimum value of ui times summation I p star I, which is just the minimum value. Okay, that's it. So now let's combine these two inequalities. I mean, for what they're worth, one is coming from the regret analysis and one is just a property of vector and probability distributions. So what do we get? So these two imply that they imply some kind of nice inequality, right? So they imply that if I look at all the iterations and I look at the inner products of the gradients with their iterates, this is at most a similar quantity, but inner product with P star plus this additive 4L square root ln d term. Okay, so let's try and sort of massage this a little so that we see a form which is which allows us to bring in the function value, right? So what do I mean? So let's so this implies that I'm going to move this inner product onto the right to the left side. So I get pt minus 1 minus p star is less than or equal to 4l times square root long t. Sorry, there should have been a t here. Okay? Okay. So now, we have some expression here. What do we make out of it? The thing we make out of it is, note that so far we haven't used convexity of the function f. And here's where we will use convexity. In particular, remember the lower envelope property of a convex function, right? So if you have any convex function, then if I draw so if this is my convex function and I take a point and let me actually draw it here. So this is my convex function, I have a point, I draw a tangent line. Then the tangent line is always below the curve. Okay? So suppose I do it at pt minus 1 and maybe p star is somewhere here. And we had this fundamental inequality of convexity, right? Which was that if f is a convex function, then f of y f of x plus the gradient of f at x and y minus x, this is kind of the tangent line, is always below the curve. We had this inequality. So let's apply this with x is pt minus 1 and y is p star. The same trick we used in the analysis of gradient descent, stochastic gradient descent several times. So let's do it one more time. So what do we get then? We get that f of pt minus 1 plus the gradient of f at pt minus 1, comma, this inner product. Oops. Okay. So notice that this is p star minus pt minus 1, so shuffling it around, this implies that the difference of the function values at my iterate with compared to the global optimum is upper bounded by this inner product of the gradients. Okay? And notice that magically this quantity here, this inner product of gradients, is exactly what we are bounding in using the regret analysis. So let's plug that in. So we get that summation t equals 1 to t of the difference in function values or the iterates compared to the global optimum is at most this t times 1t. Okay? So if I rewrite it, I get the sum of the function evaluated at all my iterates is at most t times the global optimum plus some additive term. Okay? Now, we saw something similar to this in analysis of gradient descent, where instead of getting a bound on the function value at a single point, we get a bound on sum of function values. But that's still quite useful because I can now take the minimum value of the function among my iterates. So let me define t bar as argmin t equals 1 through t of f of pt minus 1. Okay. I can also take the average and use convexity analysis just as we did in SVD, but taking the minimum also works. So then I get t times f of p bar. So since this is f of p bar is the least among all my iterates, sum of the iterates is at least t times my value, t times f of p star plus 4l squared t equal to. So this implies that I am computing a point in the simplex where the value of my function is at most the global optimum plus some term. And what is that term? It is something that is going to 0 as t goes to infinity. As the number of iterates increases, it goes to 0. And in particular, if I set t to be something which is like, let's say maybe, I think it's something like 16 times log d L squared divided by delta squared, then f of p bar is less than or equal to plus delta. So the multiplicative gradient descent algorithm gets pretty close, delta close to the global optimum, or finds a point which is delta close to the global optimum in something like a log d over delta squared iterations. And as I said, the main important thing here is the logarithmic dependence on the dimension. Whereas if you just use gradient descent with the specific normalization that we have for our function, you would get a linear in dimension dependence, which is quite bad in many scenarios. Okay. So going back, we have our corollary here. This should have been 16. Okay. It's a very precise theorem, and it's a very clean theorem. And the analysis, the algorithm is kind of, as I said, it's a multiplicative gradient descent. You can reinterpret as multiplicative weights method applied to a specific loss function. The analysis is just applying the regret bound and doing some manipulations. And this idea of using multiplicative weights method, where we define the losses in some way, shows up in many other places. Right? So there is no learning with experts game to begin with. We are just solving some completely unrelated problem. But we set up a game where there are experts, we define the losses carefully, and then magically we get something very useful. And in the last problem in the homework, you're also supposed to figure out something like this. You need to set up the loss functions in some way, such that when you apply the multiplicative weights method with those loss functions, you solve a learning problem that had nothing to do with learning with experts in the first place. And I myself used something like this in my own research as recently as a few years ago. And in the next class, we'll talk about one of the most important ideas in learning, which is boosting, which can also be interpreted in this way. So that's all for today. And in the next lecture, we'll look at one more application of multiplicative weights method, which is boosting.